This is the third part of the tutorial and illustrates how to scale the mass and check the quality, set up a simulation, modify the convergence criteria in order to obtain a more accurate solution, view periodic results, and create monitors and new planes. We need to double click on Fluent and then double click on Setup. Then we enable double precision for reducing the round-off error, and we solve in parallel to save time. The first step is to import the mass file from ISOM. Click import and then select mass. And then choose the mass file. Just to remind you that we already defined the boundary conditions in ISOM, but if you haven't done it, you can easily define them in Fluent. Click on General and then Scale in order to scale the geometry. We initially created the geometry in centimeters and now we convert it to meters. If we click on Report Quality, it will give us a report of the mesh quality in terms of aspect ratio, skewness and orthogonal quality. Click on Models and turn the energy equation on for activating heat transfer. After that, click on Viscous Model in order to specify the Turbulence Model, which is k omega SST. This model works well in flows with separation, and in Fluent the turbulence models that use omega do not require the selection of a near wall treatment. This is because the near wall treatment that is used is a Y+ insensitive method. Next, click on Materials and define air density using ideal gas law for compressible flow. Click on Change Create in order to save your modifications. As you can see, the boundary conditions are already defined here, therefore we only need to specify the inlet velocity, which is 105 meters per second, and the turbulence high density, which is 3%. Inlet temperature is 450 Kelvin. Reference values are computed from the inlet. And next we're going to modify the pressure velocity coupling. We are using the coupled algorithm, which obtains a more robust and efficient single-phase implementation for steady-state flows. For the pressure interpolation scheme, we're going to use the Presto scheme, which is often a better of choice for structured mass. Next is solution controls, where you can specify the current number. By default, Fluent monitors convergence in terms of the residuals, and here are the default values they take. We are now reducing these values in order to make the convergence criteria stricter. The simulation will now take longer to converge, but the error will be lower. We can also monitor the drag coefficient on the two surfaces of the blade. The plot option here opens a new window on the screen and shows the monitor history. In the same way, we can define a monitor for the lift coefficient. We can create a surface monitor which calculates the average Mach number on a plane downstream of the blade, and we can create a new plane or surface here, which is going to be parallel with the outlet plane. However, the horizontal position will be different. We call it downstream. In the same way, we could define a volume monitor. We could do it using this window here. Now the last step is to initialize the flow field. The initial values do not influence the accuracy of the solution. However, if they are not realistic, they will delay convergence. Here you can set up the simulation to save your results during a specific number of iterations. And now we specify the number of iterations. It is advisable to set many iterations. The simulation will stop once it is converged, and of course you can pause and resume the simulation anytime. You can also change the number of iterations without the need to initialize the solution again. Now you can see the simulation running, and this plot shows the values of the residual, which need to go down. We can see that the simulation is complete now. The residuals have gone down smoothly and they have met the convergence criteria. The exact values of the residuals can be seen here, and also the monitored coefficients and the surface monitor. If we click and drag the console icon, we can move it to the upper part and make it bigger to take a closer look. We can bring it back to the default position now. If we click on monitors now, we can view the monitored properties. This is the drag coefficient. After approximately 7 iterations, it becomes stable and therefore converged. Similarly for the lift coefficient. Here is the surface coefficient. We have the option of writing the values into a file or plotting. So the surface monitor shows the average Mach number in the field, which is 0.72. We can visualize the results using contours. Click on setup and then make sure the field option here is enabled and disable the global range. We want to use the local range of values. Otherwise it will show a range of values which are not relevant to the selected surfaces. We create a new surface here which is parallel to passage wall at a z coordinate of 0.5. We select the newly created surface and we click display. If it doesn't show, click this button and it will zoom in. Now we can only see one periodic passage, and let's select the correct surfaces first. Here we are, and now we need to show the periodic repeats to get a more realistic image of the flow. We can deselect the mid-span surface. You can see that the pressure reduces as it passes from the blades. The levels here define the levels of the contour. The more the levers, the smoother the transition of the contours. We can also plot the vectors of velocity on the mid-span surface. You can see that some of the places have more arrows and some of them have less. This is because the mesh is more fine at the dense places, at the dense regions. For example, at the trailing edge here. Let's take a look at the contours of temperature. Temperature reduces and the highest values are found on the leading edge of the blade. And the Mach number which increases as it passes from the blades. The inlet Mach number is approximately 0.3, and then it reaches as high as 0.75. You can also set up some XY plots here. In this window you can choose the variables and surfaces. If you click on the reports, you can compute some surface integrals. For example, we can compute the maximum Mach number on a specific surface. Vertex maximum simply means that this is the maximum value at a specific node. So when you select surface, it looks for all nodes and it takes the maximum value. So we can see that the maximum value on this surface is 0.78. We can also write this value to a file, and same for volume integrals here. In the same way, we can compute the average value of static pressure, for example, in the flow field.